Hello everyone, myself Michael Ravina, Associate Professor, Department of Computer Science and Engineering. The subject is CS 3551 Distributed Computing. The unit is Introduction. In this video, we are going to discuss about a model of distributed computations. That means a distributed program. The next one is a model of distributed execution. A distributed program. A distributed program is composed of a set of n asynchronous processes like P1, P2, P3, up to PI, then Pn. That means that communicate by message passing over the communication network. Here we assume that the particular each process is running on different process. The processes communicate only by using the passing messages method. Also, the processes do not share a global clock. The process execution and message transfers are asynchronous. A model of distributed execution. The process execution means sequential execution of its action. The actions are atomic, that means actions of process are three types. First one is the internal event, then second one is the send event, then third one is the receive event. Internal event means affects only the process which is executing the event. Send event means a process passes message to other processes. Receive event means a process gets messages from other processes. For a message M, let send of M denotes its send event and receive of M denotes its send and receive. That means receive event. Send of M denotes the send event. Receive of M represents the receive event. The occurrence of event changes the states of particular respective process and channels. The model of the distributed execution. The events at a process are linearly ordered by their order of occurrence. The occurrence of the particular process Pi produces a sequence of events, that is EJ1, EJ2 to up to EJ. Here EJX plus 1. It is denoted by Hi, where Hi equal to Hi tends to I. Hi is the set of event produced by the particular process Pi, and the binary relation tends to I represents the linear order on this event. The relation tends to I expresses the causal dependencies among the events of particular Pi. The send and receive events signify the flow of information between processes and establish causal dependency from the sender process to the receive process. A relation tends to message, that means that captures the causal dependency due to the message exchange. It is defined as follows, that is sent of message, sent of M tends to message. That here the tends to message defines the causal dependency between the pair of corresponding send and receive events. Then the evaluation of the particular distributed execution is depicted by a space-time diagram. The horizontal in the diagram, this is the diagram. In this diagram, the horizontal represents the particular. That means here there are P1, P2, P3. Three processes are involved. The horizontal line represents the progress of the process, and a dot indicates an event, and also a slant arrow indicates a message transfer. Since we assume that the event is an atomic, that means hence indivisible and instantaneous. In the figure, for the process P1, a second event, a message send event. Then next one is the third event is an internal event, and fourth one is the message receive event. These are illustrated in the figure. Next, the causal precedence relation. The causal precedence mean ordering of event for a particular single process is simple. They are ordered by their occurrence. Send and receive events signify the flow of information between processes and establish causal precedence between the events and the sender and receiver. For any true event EI and EJ, EI tends to EJ denotes the fact that event EJ does not directly or transitively depend on the particular EI. That is, the event EI does not causally affect event EI. The causal precedent relation is represented in this equation. Here the relations can be represented by that means the causal precedent relation induces an irreflective partial order of an event distributed that is represented to H tends to particular relations. Logical versus physical concurrency. In a distributed computation, there are two events are logical concurrent if and only if they do not causally affect each other. Physical concurrency, on the other hand, that means it has a connotation with them that the event occur on the same instant physical time. Two or more events may be logically concurrent even though they do not occur the same instant in physical time. However, if the processor speed and message delays would have been different, the execution of these events could have very well coincided in the physical time. Whether a set of logically concurrent events coincide in the physical time or not does not change the outcome of the computation. Therefore, even though a set of logically concurrent events may not have occurred at the same instant in the physical time, we can assume that these events occur at the same instant in physical time.